You're listening to KZUU 90.7 FM Pullman. We're a broadcast service of the ASWSU. I'm your host, DJ DayZ. Welcome to episode 10 of What's New Wazzu. Today, I am joined by a former professor of mine. I loved your classes and the energy you brought to them, so I'm really happy that you made the time to be here today.
My name is John Hinz. I'm in the School of Molecular Biosciences, and I teach Biology 107 here at WSU. That is my job.
How long have you been teaching that here?
I've done Bio 107 on my own since post-pandemic.
Okay.
Prior to the pandemic, I also taught the class with Dr. Bill Davis. He did most of the lectures. I actually did most of the lab preparation stuff. And then when he moved on, became vice provost, I got to take over the lectures. And I had been doing those lectures for a few years prior, since I had been teaching the summer class. So I had all the lectures in place, and so I was ready to go. Yeah.
Perfect. Right on.
Yeah.
Well, I'm glad all that worked out the way it did, because I got to take your class right after the pandemic, and it was nice to go to college and be able to be in a classroom with 500 other students and not have to wear a mask, and but also be talking about the very thing that the pandemic was all about, which is like, a biological disease, like
threw biology back at us pretty hard.
Yeah.
Gave us a couple of good lectures.
Right.
Now I have material base. It's relevant, and all of us have experienced it. And there's lots of good things in history that we can talk about that were relevant to those people. But when those people die off, or that's our grandparents' generation, we don't hear those stories anymore. It loses something, becomes much more tangible when we all suffer from it
again. And then, in a couple decades, we'll all forget about it again.
Yeah, exactly. We're going to need something new to come through to spark imaginations. Yeah.
Classic. All right. Well, now that we know that you're a professor here at WSU, let's take a few steps back. And I'd love to get to know kind of the story and the steps that got you to here, and just the exciting things, especially this science-y exciting things that have happened to you.
Yeah.
But obviously, we're a college radio station, so we'll quiz you on your music as well.
Okay, sounds good.
So I did a little research on you. I know that you got your bachelor's at Wabash College, which was a all-men's college.
That's right. Correct? Yeah, Wabash is all men. It's in Crawfordsville, Indiana. I went to Wabash in part because I grew up here in Pullman.
Did you really?
I graduated from Pullman High School back in 91. Wow. So growing up, and both my parents went to WSU. All of my aunts and uncles, both sides of the family, went to WSU. So I was raised a Cougar, but I was looking to get out of town, I think, by the end of my senior year in high school.
I get that.
And Wabash was a place where I knew I would be able to play on their football team. Okay. I could be on their track team, and I could still, focus on my studies. So it sounded like the place to go. I did not choose it because it was all men.
Yeah.
It just happened to be the place that I liked the most when I visited a variety of colleges. I knew I was going to fit in there as soon as I started meeting the guys and saw the place. So
that's cool.
I loved it. Very, very grateful I went too, because the way I teach now and the sort of the inspiration I have for the way I deliver my material is very heavily based on what I got from my professors at Wabash.
Really?
Stylistically, I'm quite different, but they were a lot more professional and much more knowledgeable about the topics. But just that whole attitude and enthusiasm, that really inspired me to see the potential in me maybe one day being a college professor.
That's cool.
I, of course, did not really have that in the books at the time, but
I always find it really interesting learning how professors gain those character traits of their teaching.
Yeah, absolutely.
That's exactly it.
That's it. And, I tumbled into teaching in a way because after I went to Wabash, I went to the University of Utah, got my PhD in oncological sciences. Right. I was very interested in research at the time. Cancer biology was very exciting. And so, my transition from there onto other things, I did not have it planned that I was going to be teaching college classes.
Okay.
So that came much later.
Okay.
I will let you get back on track, your timeline, and then we'll catch up with those topics.
Perfect. When you were at Wabash, you were learning biology.
Yeah.
That's what your degree was.
Yeah.
Did you know that you wanted to have a career studying it?
Yeah, I did. In fact, when I started college, I went in as a standard pre-med is the catchphrase that we would use because I wasn't really sure what I wanted to do. Medicine sounded good, and medicine is important. So those made sense to me. As I went through and started learning about biology in general, I became much more fascinated in the topics of biology itself and the research associated with that. So that's why, as I crept up into my junior and senior year in college, I decided that graduate school was going to be the place for me.
Okay.
That way I could do my own research and explore the depths of biology in a variety of ways.
That is very cool. Very cool. So why cancer? What was so interesting about that?
Right. So a couple of things. I went into cancer not because of the topic of cancer itself, but because the lab that I ended up joining in graduate school was in the Department of Oncological Sciences, which is cancer biology.
I see.
Now, that lab studied DNA repair. And I was with Dr. Mark Muth, great guy, very, very good advisor for me. So Dr. Muth's lab, he worked on DNA repair, specifically a repair system called mismatch repair. Now, the DNA repair systems are these groups of proteins we have in cells that monitor our DNA, recognize damage or other irregularities in it, and then repair it to make sure that that damage goes away.
Okay.
And we have to do that because if there's problems with the DNA, when our cells replicate that DNA, there is a possibility they will make changes to that DNA. Changes in the DNA sequence are mutations. And mutations are the driving force in a variety of things that affect us, including things like aging, some diseases, and of course, cancer. So that's how I ended up in the field of cancer, was that I was studying DNA repair.
Makes sense.
Since then, I have never left that field. I have bounced around DNA repair in a variety of places, including when I went to the DOE, which is coming up next in your timeline.
Yes.
And here at WSU, came here to study DNA repair as well. But there are so many different facets of DNA repair. I've been able to look at this topic from many different angles at this point. So, but it all got started at mismatch repair back in the day at Utah.
So would you say DNA repair is kind of maybe your specialty?
Yeah, absolutely. Okay. DNA repair is my specialty. And,
gotcha.
And you know, most people in the field of DNA repair are pretty familiar with most facets of DNA repair, even though DNA repair can be broken down into a couple of systems that recognize certain types of damage, and then some systems that just recognize breaks, and then some systems that do other special things.
Okay.
And so, but most of the time when you're in a field like DNA repair, you're quite familiar with many of the facets of this, and you specialize in one of those particular pathways.
I see what you're saying.
And so, so obviously mismatch repair was the one I was in at the beginning, but slowly moved my way into these other ones.
Which facet did you focus your PhD thesis on?
Definitely mismatch repair, and I started creeping into what's called double-strand break repair near the end of my thesis. So mismatch repair is looking for mistakes that the DNA polymerase, that is the enzyme that replicates DNA, the DNA polymerase makes mistakes on occasion. And so there's a system in the cell that recognizes that, corrects those errors. That's mismatch repair.
Gotcha.
Without mismatch repair, we would have thousands of changes to the DNA sequence every time our cells divide. With mismatch repair, we're down to 6 to 10 mutations per cell division. That's not so bad, although we do go through 100 trillion cell divisions in our lifespan. So when you do the math there, you see why it is that we get weird things happening as we get older. But I started to creep into double-strand break repair at the end of my thesis. Double-strand break repair are the repair pathways that recognize breaks in chromosomes and try to get those patched together with as little trouble as possible, because when you break DNA, there's some dirty ends that need to be cleaned up. And when you're cleaning up the ends on a piece of information, it'd be like splicing a tape here. You get a break in the tape. You don't want to trim the tape too far back on either side before you merge it back together, or you're going to miss information. If that's in the middle of a gene, you've messed up a gene anyway. Right. So double-strand break repair is all about trying to repair those breaks. But breaks are really bad for the cell, basically fatal. And so the cell will get desperate at times, and it's going to put that DNA back together any way that it can. Mismatch repair, not usually an issue. Mismatch repair takes care of itself. You get in double-strand break repair, it gets ugly. But it's desperate times when you're repairing double-strand breaks. And this is what got me interested in radiation biology, which is why after I got my PhD, I was looking at labs that studied break repair and radiation damage. And that's what took me to the Department of Energy.
Perfect segue. I would love to talk about that.
Yeah.
Okay. So very, very interesting. Double strand break repair.
Mm-hmm.
Okay. So back in class and lecture, you always talk about how you used to work for the Department of Energy, and you always you get the entire class very interested because you tell us it's top secret, the things that you would work on.
Right. I didn't work on any projects that were classified in that top secret category.
Okay.
It was of course, being on site, you're required to have clearance anyway. That allows us to have certain types of discussions and certain materials available. Mm-hmm. As you get pulled into other projects, your clearance may have to change.
Yes.
And so I was actually applying for the highest level of clearance just before I took my job here at WSU.
Really?
And in fact, I was going through the background checks at the time because the intention was for me to continue to work on projects there that would have different levels of classification.
Gotcha.
However, I actually timed it just right and got to come to WSU before I started working on any of those projects. Not that I was against them, but that was not the direction I saw my career going. Okay. I became much more interested in academic science and less interested in the government part of the science.
Gotcha.
It's very similar science. It's just the attitude and direction associated with that science, and whether or not you can publish it is different between
Makes sense.
At a university versus an energy lab.
Makes sense.
So the Department of Energy has for a long time been interested in the concepts of DNA repair.
So that doesn't make intuitive sense.
Right. I'll tell you why. Because the Department of Energy is responsible for a variety of things. One of them being, of course, how it is that we're going to power this country.
Right.
And then the repercussions of that. Well, we have been creeping towards the use of nuclear energy for a long time. And with nuclear energy, we, of course, have the potential of having exposures to radiation. Because a key feature of using radioactivity and energy is that there's going to be this stuff that's going to come out and interact with people.
Right.
And so nuclear energy, while it's probably is the energy of the future, it has these side effects that are problematic. The reason that radiation is bad for us is because it damages DNA. Now, it damages other things in the cells as well. But the thing that really hurts us from being exposed to radiation is the fact that it causes damage to DNA. Damage to DNA thus can then lead to mutations or cell death. And that's things we're trying to avoid as large, complex, multicellular organisms. We want all of our cells to be on board.
On the same page.
All the same page here. Yeah, exactly. We don't want their information to change. They need to keep the playbook that they started with.
I see.
And so the Department of Energy understands that this is a repercussion of the use of energies that we would use in the future.
Okay.
The other thing is that we have this massive nuclear arsenal, as do other countries. The deployment of that arsenal has effects other than just the localized concentration of massive heat and pressure in the target zones. We're going to have a lot of other issues, radioactive fallout, these sorts of things.
Right.
We need to understand how all that's going to impact us as well before we even touch a button where we're going to launch something. And so these are the early days, right? This is like the 1950s, where we're just now getting into the arms race, the nuclear arms race. We're just now starting to understand the real power we have by splitting the atom, and then the side effects, this radioactivity. And so understanding how it is that it affects organisms, very important for the Department of Energy.
I see.
And as it turns out then, organisms have evolved these systems, a variety of genes that encode proteins that recognize damage to DNA. These are our DNA repair systems.
Right.
And so understanding how DNA repair works in the context of radiation, crucial. And that's why Department of Energy is interested in DNA repair, and in particular, double-strand break repair, because the one type of damage that radiation can do that's the most dangerous for us is the breaks that it causes to the DNA. It causes other types of damage to the DNA as well, but many of this DNA repair systems we've evolved have evolved to deal with some of that damage, but not in massive amounts when we're talking about creating breaks in the DNA. So we need to understand what the thresholds are. And in the early days of the DOE, it would have been something more simple like you take a cow or something and you irradiate it with a certain dose of radiation, and at some point, some of the cows start dying from when you hit certain doses. So we get an idea of what the lethality is on an organism. They stopped irradiating cows and goats and things when we finally developed tissue culture, because in tissue culture, we can take cells from people or from any animal, grow it in culture, irradiate those cells, and then do many different measurements.
Without having to kill it.
Without having to kill anything.
Right.
Exactly. And so now tissue culture didn't come about until like the 60s and 70s, where it really got going well, and probably really we could manipulate it the most in the 80s. At that point, then, of course, we're moving on to exposing cells to radiation. This is still well before I'm in any of these fields here.
Right.
In the way, I'm still a kid at this time. But when the Human Genome Project started, the Human Genome Project was the project that was started back in the 90s, where the goal was to sequence the entirety of the human genome.
Right.
Our sequencing technology wasn't so good that we could just jump in and sequence all the chromosomes. We had to start small and build our way up. Now, our sequencing technology is very good. So we can take an organism, sequence, it's like a prokaryote, a bacterium. We can sequence this genome in an afternoon and have all the information we need on it. Couldn't do that back in the 90s. Yeah, it's very good, very good. So the Department of Energy was the group that spearheaded the sequencing of the Human Genome Project. And the first chromosome sequenced was, the first human chromosome sequenced in its entirety was chromosome 19. And there were a couple of reasons for that. Number one, it's one of the smaller chromosomes, so as a reasonable target to shoot for. You start small and work your way up.
Right.
The other reason 19 was important to the Department of Energy was because we knew that there were genes that were encoded on chromosome 19 that were associated with DNA repair.
Makes sense.
And the Department of Energy was interested in knowing what those genes were or what they did.
Was it true that the genome that they selected was one of the people heading the project?
Yes, as I understand it, that would be one of the genomes sampled. The guy's name escapes me right now. But the human genome composition, as I understand it, is actually an assemblage of about 50 individuals.
Okay.
And so that we get some breadth in there, because mind you, any one individual won't actually have the same genome composition as any other individual unless that individual has an identical twin.
Right.
So having lots of different genomes in there is important. And many of these changes in our genome from person to person, these are small changes. They're we refer to as polymorphisms. There's just a different version of the gene. They're all caused by mutations. They're all still mutations, but usually we reserve the term mutation when we're talking about people having a mutation. We usually reserve the term mutation for them having a change in a DNA sequence that impacts that person negatively in some way, because it's really causing a problem for a gene, like the gene's not functioning normally.
Right.
But most of us have polymorphisms, which means we have a different version of the genes from each other, but both of our versions of the genes are functional. They're making proteins that do the job they're supposed to do.
Right.
Just all of us have slightly different versions of these proteins, and thus we don't all look alike, and we all respond differently to various things in the environment.
Would two identical twins also have technically slightly different genes because they've gone through different mutations?
I would look at it this way. Technically, every cell in the body of any individual has slightly different changes.
Okay.
Now, if we're talking about what it is that a law enforcement agency would use to determine whether or not an individual had left things at a crime scene, evidence, like DNA evidence,
right?
They don't sequence the entire genome of the individual. They pick these 13 different locations in the human genome that tend to have a lot of variability from person to person, but not so much that you'd be different from your mom or your dad's version of the chromosomes you got from them. And that's how it is that we just select these different spots in the genome, and that those are the things that we look for. And
gotcha.
But there, your chances of being 100% overlap with another person there, just in those 13 different genes would be, and you have two copies of each one because you got one from mom and one from dad. This is how they know who your parents are when you do these as well. The chance of you having the same as another individual on the planet is about 1 in a billion. So that's sufficient. So you wouldn't actually need to go through the effort of sequencing every chromosome of an individual and being like, wait a minute, this is twin A versus twin B. And really, you can't tell apart identical twins using the technologies we do now.
Okay.
It's
very interesting.
Yeah.
Very interesting. So, okay. So now we understand why the Department of Energy is focusing on DNA repair. Where do you and the Department of Energy meet in this research?
Right. So when I was getting near the end of my PhD, I started looking for places to do a postdoc. A postdoc is the position you take typically after you get your PhD, especially if you want to stay in academic science, although there is postdoc positions in the industry as well if you want to work for a company. But the postdoc position is a transition position from when you've been a PhD student to when you want to have your own lab at some facility somewhere. So I did my postdoc at the Livermore Labs because there was a guy, Dr. Larry Thompson, who was at the Livermore Labs, who had been the discoverer of multiple proteins associated with one of the double-strand break repair systems. And he had been at the Livermore Labs for a very long time. Most of his career had been at the Livermore Labs. Sure. He didn't do classified research. He was at the Livermore Labs because of DOE's interest in those topics. And so, but he'd been there a long time. I had seen his work. I referenced him a number of times, contacted him, and sure enough, he was looking for a postdoc right about the time I was doing it. So fate sort of took me to Northern California at that point, and that's at the Lawrence Livermore National Labs, which is in Livermore, California, and so then I got a chance to work at the Livermore Labs. The postdoc position is only a 3-year position. So once I was there for 3 years, I actually transitioned to what's called a biomedical scientist, which is like their generic term for just anyone working in the department in the biology sciences. And going from there. And I was there for another 3 years, continuing to work on projects with Larry before I had the opportunity to spring here to WSU.
Gotcha.
But that overlap between my work in DNA repair and the Department of Energy comes down to the fact that I ended up joining a lab that studied DNA repair that was the Department of Energy facility. But Larry had started his lab at the DOE in part because of DOE's interest classically, many, many years before, back in the 70s and 80s, in their interest in DNA repair. So
interesting.
Yeah.
So was your research always focused on understanding the process? Was it ever focused on like manipulating it or changing?
Right. I think understanding would be the key thing. There was always this, we don't know most of the time when you go into a research project, your goal is to understand what's going on based on something that you've seen before. It's actually the scientific method. It's a proper scientific method. You witness something in the environment or under some condition, and you make a hypothesis as to why it is it does that. And then you test the hypothesis by manipulating the system in a variety of ways. So one of the things that one of the programs, projects that we worked on at the Livermore Labs was we had this, there's this disease, an inherited disease called Fanconi anemia. And the people who inherit Fanconi anemia, they frequently succumb to the anemia part of the disease. They get bone marrow failure at a fairly young age. Now, they can get bone marrow transplants. And if you get a bone marrow transplant, that actually rescues you from your own body's inability to make blood cells. So bone marrow transplants very useful for these kids. That lets them survive. Otherwise, the lifespan is like 5 years on average. Very short.
Yes.
So, but people who would then receive bone marrow transplants who had this Fanconi anemia, they would very frequently get cancer at some point in their 20s. Now, people who get cancer early in their lifespan tend to have other things going on, right? Like the chance of you getting cancer in the age of 20 is pretty unlikely unless you've had an exposure to something or unless you've inherited something that predisposes you to cancer. So Fanconi anemia is clearly what we would consider to be a cancer predisposition disease. Yes, the anemia part is the lethal part for many of these kids. But once you get them past that hurdle and you get them the treatment they need there, they got to deal with the cancers.
There's a new obstacle.
There's a new obstacle that hits them very, very hard in their 20s. And so we wanted to understand, well, all these genes, and Fanconi anemia disease can be caused by mutations in several different genes. There's 14 or 15 of them, where if you have a defective version of both copies of the gene, because remember, you get one copy from mom and one copy from dad.
Right.
And unless it's acting in a dominant manner, you actually have to get a bad copy from both parents.
So it's recessive.
So it's recessive, absolutely. Okay. So glad you were paying attention to genetics about 107. So somebody is homozygous recessive for one of these genes. They will suffer from this condition. We wanted to understand what the proteins that were encoded by these genes actually did for people. So we got into Fanconi anemia. Now, as it turned out, Dr. Thompson, the guy I worked for, he had actually discovered the FANG-G gene. FANG-G is the version in humans. Had discovered it in Chinese hamster ovary cells a number of years before. And at the time it was called XRCC9, I believe, or something like that, which stands for X-ray cross-complementing. And what that simply means is that they had these cells that were, they had or treated them with some mutagen to sort of randomly mutagenize genes. And then they looked for cells that were sensitive to radiation. And if you found a cell that was sensitive to radiation after you had mutagenized it, then you probably caused a mutation in a gene that was important for saving that cell from radiation. Right. Cells protect themselves from radiation when they can. And if you give some random mutations and now you have a cell that can't protect itself the same way, you hit one of those genes.
I think I see where this is going now.
So then the idea is, okay, well, what genes are out there that could rescue this cell? If we gave it some genes, what genes might rescue it? And so what they would do is they would take these sensitive Chinese hamster ovary genes, and they would put into they'd put into those cells sections of human chromosomes. And then they would see what section of a human chromosome would rescue this radiation-sensitive Chinese hamster cell from being radiation-sensitive and make it back to a normal cell. Because we're complementing the deficiency the Chinese hamster cell has with some section of a human chromosome.
I see.
And that section of the human chromosome then must contain the gene that is lacking in these things. Anyway, what it comes down to is they discovered that there was this gene on human chromosomes that would rescue Chinese hamster ovary cells that were sensitive to radiation, and so they named it and they went on from there. And then, as it turns out, there are people who are defective in this gene, and they have the disease Fanconi anemia. So in fact, the Fanconi anemia, some of these genes had been discovered prior to us realizing what the gene was in humans that was causing this disease.
So is it possible to complement that deficiency in humans with other human genes?
Absolutely. So it gets tricky here because when you're born with a mutation that's problematic for you, it's in every cell of your body. Right? So we could try to get a normal version of that gene into any cell in your body. That cell is rescued. You have 50 trillion cells. Right. So that's why it is that when we're talking about doing gene therapy, there's a couple of different ways of doing it. One thing is that if you do gene therapy on a fetus, something that has a much smaller number of cells, well, any cells that you manipulate in a fetus, those cells have now been rescued. That could be a big chunk of the person, down the line when that thing develops. So the earlier you get it in embryogenesis and you do your intervention there, the larger fraction of the cells that embryo will eventually develop into full human parts, the larger fraction of those would be complemented. You would have what you needed in there.
Okay.
So when we're talking about gene therapy, that's one way of thinking about it, is that we can, if you discover early enough in a child in utero that there's a problem, you can intervene early and get a big population of their cells corrected. The other thing to consider is for Fanconi anemia patients, while they will get cancer in a variety of cells in their body because of the fact that every cell in their body is missing that crucial gene protecting them from cancer, let's say you wanted to get them through the blood, the anemia part of the disease. Another thing you can do is you can take cells from a person, stem cells, for example, and you can augment those stem cells and then put them back in the person. Now you've actually replenished a population of cells that are the cells responsible for replenishing cells that die, and they're going to get replaced with these stem cells that are now differentiating to become these other cells. Well, these cells are a subset of cells in the body that actually are fully functional, that no longer have that particular mutation or whatever the issue is. So you can do that as well. So you can take bone marrow from people, treat the bone marrow in a way that changes the problem, eliminates the disease, and then put their bone marrow back in them. That is corrected bone marrow. That's a bone marrow transplant that doesn't require another donor.
Interesting.
You don't need somebody to be compatible when you get your own bone marrow back. All you need to do is have the bone marrow that you gave them, which is just chock full of stem cells. They'll take those stem cells, they'll get some of those corrected in some way, do some appropriate tests. You got to watch out, because when you're manipulating genomes, you don't want to make changes in the DNA other than very specifically the change you want to make. Otherwise, you could give them a very different condition, some other cancer predisposition or something else. You don't want to put rogue cells on.
Let's avoid that.
Let's avoid that, exactly. So they're careful. They have some controls. They can do some manipulation of cells. They can put those cells back in the person. So you're your own donor in that case, which is perfect. Yeah, which is exactly what you need. And then you use those cells for whatever. So they're tinkering with a variety of tissue types now. Bone marrow is easy because it's easy to pull out. It's rich with stem cells. Every cell that's going to be any version of a blood cell in your body is coming from your bone marrow. So you can correct many different blood-associated diseases, genetic diseases by doing corrections like this.
I see. So this kind of, I guess, would be the same avenues that you would take to cure cancer.
Yeah.
Potentially.
Could be. So I think the key is curing cancer gets tricky because cancer is such a broad range of diseases. Every cancer that anyone gets is going to be different from any cancer that anyone else gets. We get them in the same tissues, and we can, breast cancer is a common cancer, but any person's breast cancer will be different from any other person's breast cancer. The routes they took to become breast cancers, the mutations they get and whatnot, may be very similar between the two, but no two cancers are the same, which means finding a cure for cancer is a little bit, that's sort of a tricky way of putting it. Probably more appropriate would be being able to manage the disease of cancer, because once you have a cancerous population of cells in your body, eliminating that can be quite tricky. But if you can have the right therapies that make it so that cancer never goes metastatic, or that cancer, even if it is metastatic, doesn't actually grow out into tumors later down the road, well, then you've actually treated the illness.
And you can live with it.
Yeah, you can live with it. Yeah, you just live with it and you don't die from it.
Gotcha.
We're all going to die from something. The key with cancer therapy is we don't want you to die from cancer.
Right.
Something else is going to have to.
That's the very important shift in like how you deal with solving cancer. Because in my life, I always thought like there's a cure out there. You know, that's what people talk about, like the cure for cancer. But we have many different tools that we can use to kill cells. We've been able to kill cells for a long time. Different drugs. We can use radiation. In fact, radiation is very useful in certain types of cancer treatment. And so, and chemotherapy, very good. In fact, chemotherapy is useful because by putting a chemical in a person's system, you know that drug goes everywhere in their body, which is where any of these cells could be hiding depending on how far the cancer is progressed. That's why we do chemotherapy, is because sometimes you see someone, they've got a tumor, maybe you can pull that tumor out surgically, or maybe you can just smash that tumor with radiation, because when it's a tumor, you have a target. So a target's easy. The problem is that once cells start breaking away from that and going to distant locations, and that's metastasis, it becomes a lot harder to find those suckers. In fact, they kind of have to grow out to become target tumors themselves. By then, now that cancer is all over the place. So instead, frequently, even if you could get it with surgery or with radiation treatment, you will still be given a chemotherapeutic cocktail just in case some of those cells went somewhere else, because they're not going to be part of the surgery and they're not going to be part of the radiation. And then they could be able to potentially continue growing.
And then exactly. Yeah, exactly. And then they become some other tumor. It becomes problematic.
Gotcha.
And there's always risks associated with treating someone with drugs or with radiation. One of those risks being you can trigger other cells to become cancerous later on their lifespan, because many cancer treatment drugs cause mutations in cells. It's the exact crap we tell you not to expose yourself to in general. And then we do it, we use it, but
fighting fire with fire.
We're fighting fire with fire. Exactly. When you fight fire with fire, you start other fires. But the key is that you can buy yourself 20 years by putting out the one fire with a backfire that's later going to be problematic for you. I say you have to go from there. And so yes, we have been able to kill cells for a long time. The very tricky part has always been targeting, because if you can target cancer cells, have the drugs that you put in go in and actually go after the cells you're looking for, then that means you can scale way back on how much you give the person. You don't have to give them doses where every cell in their body is being punished. You give them the doses that just punish the cells you're trying to target.
I see.
And now we're getting into things like immunotherapy, which is becoming much more trendy, because if you know the difference between the cancer cell and the other cells in the body, you use that tag as the target. That's what we want the drug or the other version of treatment, of whatever treatment we're using. That's what we want it to look for. That's where we want it to go.
Right.
And then you're targeting things. It's a much better way than the carpet bombing that we do when we give drugs otherwise. And so we definitely are progressing in those ways. And because we're progressing in those ways, we have types of cancers now that for 20 or 30 years we could diagnose, and then our ability to survive cancer got better and better over the years because our diagnoses got better, not because our treatments got better. Because the treatment is always carpet bombing.
It's always the same.
It's just whether or not you know when to do the bombing. And if you do the bombing early enough, then usually you do a better job of treating it. And so as we've gotten better at detecting cancers over time, we're getting better at treating it simply because we're detecting it better, not because we have better modes of killing the tumors. Now we're very good at detecting cancers if we're looking for them. Not good enough, but much better than we used to be. But now also we're starting to have therapies that are much more characterized towards the type of tumor you're going after. That makes it much more efficient, because now not only do you detect it early, potentially before it has become a problem at all, but now also you know that your treatment is going to go in and really punish the one zone without hitting the rest of the body.
Right. I see. Would you say that the causes of cancer, like environmental causes of cancer, have increased or decreased with time?
Yeah. So I would say that probably in general, and I don't know the literature well on pollutants, but in general, I think we're always creeping up in the risks associated with living in the environments we live in. Right. You don't have but one environment to live in, because we're breathing in more chemicals in the air, and we're just exposed to other things that we hadn't been exposed to before. And mind you, if we had evolved in the presence of lots of fossil fuels being burned and smoking cigarettes all the time, and lead paints on the wall and all the other things in the environment, well then we would actually be much more robust to those. But those things have been going up, and human evolution does not keep up with that. We're not selecting against that yet. So yeah, I would say that in general, the environments, probably all water environments on the planet, obviously the atmosphere, in general is creeping up to be more problematic for us, and thus likely to be a cause of things like cancer. And there are other diseases associated with breathing bad air as well. So that's not the only thing. But cardiovascular diseases are increasing as well because of that. However, I say that, but our behavior and thus our intentional exposures to some things have changed over the years. Because once we started doing the anti-smoking campaigns, because for a long time, the tobacco industry would have kept quiet the fact that their product, which is very, very addictive, is also very dangerous for people. Once it became obvious that smoking tobacco products is really dangerous for people, people started backing off of using those products. Yeah. And because they started backing off of using those products, then of course the diseases associated with the use of those products would begin to drop as well. Right. And smoking, is a very dangerous thing to do, not just because of your increased rate in cancer, which is quite high. It's threefold higher if you're a smoker than not. That's a sort of a general number out there. But also the cardiovascular disease, the heart disease, the thing that kills actually more people than cancer in the U.S. every year, is also exacerbated greatly by smoking. So smoking is actually an important factor in the two things that kill us the most in the environment. And so,
interesting.
So we have control over our environmental exposures. But the problem with the tobacco products is actually, I would argue, it's not the tobacco. Yes, combustion of tobacco makes a bunch of cancer chemicals that you're breathing in and you're exposing your lungs to, and it goes in your bloodstream. That's why you get cancers all over the place when you're a smoker. But to me, the actual problem is the addiction component. Because if we smoked one cigarette a day, let's just say you and I were in the mood for a cigarette after this interview. Okay, one additional cigarette a day doesn't really pose a huge risk. In fact, one cigarette a day is sort of probably roughly the amount of carcinogens we breathe in over the course of an entire day, which means we just went from 1 day of exposure to 2 days of exposure. Right. But people who are addicted to a product like this don't get to do one cigarette a day and don't get a day off. So they're going to do many, many cigarettes a day over time. And this is why it is that it's going to creep up on them.
Seems exponentially worse.
Yeah, it's much worse. It's much worse. If they got rid of the nicotine part of these smoking products, then I wouldn't complain about the smoking products at all. The nicotine part is the dangerous part. The nicotine part is the part they will never get rid of, because that's what assures the sales of those products.
Right.
That's fact, by the way. That's not me being high horsed here, because that's, I've been exposed to those products before. I understand the nature of addiction.
Yeah.
And so people need to control that. And that's a very difficult thing to control. And thus we put ourselves at higher risk when we, fall into those things.
So one way to protect yourself from cancer would be to manage your habits and your behaviors.
Absolutely. Habits and behaviors. Here's an interesting statistic. By not smoking, you reduce your chance of dying from cancer by a third. You cut it into a third. If you exercise regularly, you cut it down by another third, which means your chance of getting cancer goes down by 1/9, but roughly to about 10% of your of the population if you exercise regularly and you do not smoke. And of course, healthy eating blends in there as well, definitely plays a role. But that's the one I can't really brag about, because I don't smoke and I exercise regularly, but I don't eat healthy. So I gotta choose my vice.
Yeah.
My vice is I just won't eat healthy.
I like that.
I do on occasion. But other than that, so you got to pick, you get to pick and choose from there. But really, regular exercise and not smoking, you're taking care of a lot of those cancer risks that we talk about all the time anyway.
Interesting. There's one other small cancer avoiding habit that people do and don't do, sunscreen.
Yes.
Is it important?
Very important. Very important to wear the sunscreen. And that's true. I mean, the most abundant cancer that gets diagnosed in the U.S. is going to be one of a few types of skin cancers.
Right.
The most dangerous type of skin cancer is the melanoma. Right. We have cells in our skin called melanocytes. The melanocytes release melanin when we're exposed to sunlight, and that's what makes us go tan. The melanin changes our color. Some people have very, very high melanin levels in their skin. Because of that, they actually have their own sunscreen. Should they wear additional sunscreen? Absolutely, because you're trying to reduce your exposure to ultraviolet light as much as possible.
Okay.
Ultraviolet light causes damage to DNA. And it can get through the dead layers of skin that we have and get into your live skin layers. Ultraviolet light, though, isn't going to cause cancers in places that don't reach, that where the ultraviolet light can't reach. So we tend to only get skin cancers from ultraviolet light. It's where the UV light can hit you is where the problems are. And so by getting yourself sunscreen, either nature's sunscreen with some nice dark pigmentation or applying your own sunscreen on there, you eliminate the amount of ultraviolet light that comes in and bombards you. Now, these melanocytes in our cell, in our skin, no matter how many melanocytes you get, the melanocytes have the potential of getting mutations just like other skin cells do. The problem with melanocytes, the thing that makes them dangerous about them getting the mutations that turn them into cancers, is melanocytes are a mobile cell population already. So a melanocyte's job is also to creep around and do things within the cells of your skin. So when a cell that already has all of the tools it needs to move around starts acquiring the mutations it also needs to grow out of control, which is what a tumor is.
Right.
Well, you've already handed it one of the check boxes you need to check for a tumor to kill you, which is mobility.
Right.
The ability to move around and hide and do what it needs to do. And so melanocytes start with that weapon. And so when they go mutant, they become problematic. Many of our skin cells, the reason we don't tend to die from skin cancers other than melanomas is because the skin cells, not only do they not really move around, and they can go deep and they can kill you eventually. Not only do they tend to move around, but because they're on our skin, we see them. And remember I said that detection was an important part of cancer treatment?
Right.
Well, hell, you're going to see a tumor growing on your skin. You'll ask your doctor, they'll take a look. They'll be like, you know what? This is pretty easy to get rid of. They sometimes don't even determine whether or not it's really cancerous. If it's something easy to cut out, sometimes they'll just do the cut.
Like a mole or something.
Like a mole, exactly. And they can, we have moles, and moles are a normal part of our bodies. Some people have lots of moles. Those moles are not melanomas. Yes, they have some melanin expression, and then they look really dark. But many of those are actually quite reasonable for us. But there are some rules you can follow to determine whether or not a mole is potentially a melanocyte that has laid its turf out and started really growing out on you. And hey, if you see one of those, you're lucky that melanocyte decided to stop in a place that you can see, because some of these things will go deep and they form the tumors in there. You're not going to see those until they reach the surface or they become an actual mass that you can detect.
Right.
And so, but there's some rules that you can follow in general when you're looking at a mole to decide whether or not that mole is problematic. The easiest thing to do is go to a physician and just say, hey, if you have an annual physical exam, you can just say, hey, will you do a quick mole check on the moles on my back and a few other places and just take a look. And they're just looking for certain features of that mole that make it more likely that it's probably something that's not a mole.
Like being asymmetrical.
Asymmetrical, very good example. If the borders are rough rather than nice and smooth, it's actually the ABCDE rule is what they fall. A is the asymmetry. B is the borders. C is the color. Does it have more than one color?
Right.
If it's just uniform in color, it may not actually be an issue. C is color. D is diameter. And the diameter they usually think about is like, I want to say it's like, I don't remember. It's been a while now. It's like 5 millimeters.
Yeah.
Anything smaller than 5 millimeters, probably not an issue. E in the ABCDE is, I have no idea. I don't remember. E was added later. Like when I used to do it, it was like ABCD.
Sure.
So whatever E is, there it is as well. Although I will say that anytime you have something on your body that grows really, really quickly, it's not a bad idea to get that looked at because our cells have a certain pace to their growth. And because we're a multicellular organism, the cells should be under the control and at the pace of the other cells in the organism. So anything grows out of control, probably not a bad idea to get the doctor to take a peek.
Good to know. And all right, so I'll start wearing more sunscreen then.
Yeah, good idea. I try to remember, but even me who studied the DNA repair system here at WSU, one of the DNA repair systems we studied was called nucleotide excision repair. That repair system is the one that recognizes the damage caused by ultraviolet light in our skin.
Interesting.
So hell, I even studied that thing. I still will forget to put sunscreen on occasion. And mind you, like when I was young, I didn't have to worry about the top of my head. But you forget as you get older that you get thinner hair, and your hair plays a very important role in protecting the top of your head from exposures like sun. So now I get that hot spot on the top. I feel like, I forgot. I got to wear a hat now.
That's funny. That's funny. My dad deals with that often.
Yeah. It's the way it is for us.
All right, so I've got one more question, sciencey question I'd love to ask you before I ask some more personal questions.
Sure.
But what do you think the place is for AI in the future of oncology? And
very useful. AI right now, the big advantage of AI is that it's pretty fast. Yeah. So if you wanted to put together a group of knowledge and really hit like the bullet points of what are we looking for here, well, the AI will do it if you just type in a sentence, as opposed to you pulling together a bunch of your colleagues and then brainstorming this.
Okay.
Now, AI is not terribly dependable because it really depends on what the sources of information are that AI can use. So when you're putting together a list of, let's say someone was to ask, hey, give me a list of things that you think are important for someone to avoid an automobile accident or whatever, or suffering from injuries in an automobile accident. And you're going to start listing off things right away that you know and things that you practice on, wearing a seatbelt and paying attention, not being tired, and X, Y, and Z. Okay,
right.
Now, you're getting that information from the data bank that you store in your brain. And yes, as you go through and reason, you'll find that there are a bunch of things on the list, and you may forget a thing or two that's important, but you're going to generate a list, and it's going to have 4 or 5 good things. And all of them are going to be accurate to the best of your knowledge. Now, what AI can do is in a much shorter period of time, give you a list of 50 things. And each one of those 50 things, somewhere in the AI's knowledge zone, which for some AI is just the internet.
Right.
The AI is pulling that information out and putting it in the list. Now, the AI believes, and it doesn't believe anything, it's an artificial intelligence, but the AI is putting in that list because it sees that as a legitimate part of the question that you asked it or the command that you gave it. But the AI is not really capable yet of filtering out the things that are not really associated with what you're asking, because you're not asking for things that are part of conspiracy theories, or you're not asking for things that are particularly rare. And you can specify things for AI. So AI is smart enough to filter certain things out. But right now, the risk with AI is that AI is pulling from a variety of sources. Not all those sources have been vetted in the same way.
So it's unable to really fact check itself and could spread misinformation.
Exactly. So when we're talking about a diagnosis, let's say a doctor wants to use AI to help diagnose. Great idea, because I tell you what, a doctor knows only so much. And then anything else they would want to gain from that, they would ask colleagues or they'd go to the internet anyway. And, Google is actually just a search program that you're using to do basically what AI is doing anyway. But AI does a little bit of filtering because it knows specifically what you're asking. I think the problem with AI is it doesn't filter its own information out.
Right.
So AI can give you a lot and Google can give you a lot. But when you're getting the information from Google, then you do the next round of sorting where you're like, well, that's not a legitimate source. This is a publication, right? And I'm not saying that doctors use Google, by the way. Doctors will probably actually use PubMed, some of these other things that are medically associated. It's all going to be research that has been peer reviewed. And so it's understood that these are the appropriate things. When you restrict your AI to sources that you consider to be dependable sources, that AI actually probably has a very powerful ability to give you output. Will it be wrong on occasion? Absolutely. Can a physician be wrong on occasion? Absolutely. But the AI is going to be very fast, very fast. And it's going to reach into crevices of knowledge that many physicians wouldn't know or have never experienced. And so AI could be very useful in that regard. I think as AI improves, while you will never be able to remove the physician part of the experience of medicine, I think physicians will learn to use AI as a trusted companion, just like you would if you had sort of an expert in every field ready to call on the phone at any time. You're going to be able to use AI for that. So it makes everybody a lot more efficient.
Cool. So cool. That's a hopeful future for its application.
Yeah, absolutely. There's for every technology, there are applications that are beneficial, and then there are malevolent applications as well. And so it's always an arms race.
Yeah.
And we've seen that with everything from the development of harnessing the power of the atom all the way up to manipulating the genomes of organisms. Many of those things have been very beneficial to us, and some of those things have made very dangerous to live on this planet.
And that's why the field of ethics is so important within every other interdisciplinary field, right?
Yep, absolutely.
That's cool.
Absolutely.
Well, thank you so much for sharing so much about your knowledge. It is a treat to listen. I don't know. I find it very interesting. So
thanks, Chris.
So thank you for sharing.
Yeah, my pleasure.
But I'd love to ask you a few questions before we end the show.
Sure.
Just about yourself.
Sure.
What kind of music do you listen to? I see you walk into the rec frequently.
Oh yeah.
And you're always listening to music. And you're working out, which you mentioned earlier.
So
I'd love to know what you listen to.
Yeah. So I listen to different genres of music depending on what it is that I'm doing.
Okay.
So, and by the way, I want to point out that when I went to college, which was between the years of 91 and 95, I graduated from Wabash in 95. That was when the grunge music was starting to come on scene.
Okay.
And that is when you started having the style of music that we would normally consider to be counterculture to actually become the most popular type of music out, right? Which is actually sort of the antithesis of the counterculture thing, but it became very popular. And so for me, going into college, the bands that were becoming big, that were quite popular, many of them based out of the state of Washington, you had Nirvana, you had Pearl Jam, you had Soundgarden. And by the way, I went to a Soundgarden concert when I was a sophomore in high school here at the Cub.
No way!
Yeah. It was awesome.
Wow.
It was really good. Soundgarden was just getting going, And so in fact, the band that opened for them at that concert was a local Pullman High School band. They opened for Soundgarden. And
that's funny.
So anyway, great music back then. I still really like that music and that style of music.
Okay.
And so, but now we consider that music to be classic rock, which to me is like, what the hell? I was in college when that stuff came out. Okay, so now you listen to that kind of music on classic rock stations. And they'll still play that music on alternative stations as well. If you're going to pick genres, they fall into that as well. But now you're playing that kind of stuff on classic rock. I'm a huge fan of classic rock. And in fact, I'm a fan of classic rock that was the classic rock when I was in college, right? So we're talking about things like Led Zeppelin,
right,
and The Doors, and Rush, and a wide variety of music types there. I still listen to that stuff. That is fantastic music for me to listen to in the car. Like when I'm driving long distances, love that style of music.
Okay.
Great driving music. Reminds me
it's good road trip music.
Good road trip music. I got lots of good memories associated with all those songs as well. When I'm walking across campus or I'm going to the gym, I actually tend to listen more to contemporary music.
Okay.
Now, when I say contemporary music, I still been within the last 15 years, but the reason is that contemporary music is paced up a little bit, and it's even when they produce it, it's produced at a louder volume than these other things. In fact, if you have a playlist like mine on the phone, you will find yourself adjusting the volume on occasion because the music that was produced 20, 30 years ago, that music is not produced at the same volume. And so you get these volume shifts where it's like, all of a sudden the Katy Perry song comes on. You gotta dial that back.
Totally.
It's way too high in volume. But the higher volume, the faster pace, that kind of music I actually find much more useful when I'm trying to maintain that pace of life myself.
Right.
Which is why when I go to the gym, I listen to music on my phone. And it's music that I purchased, but that music I was exposed to within the past 10 to 15 years. Mm-hmm. And it's music that I may have heard on the radio or music that somebody may have suggested, or maybe I saw a video and I saw this artist and I thought, what else does this artist do? And then I went from there. And so that's the kind of music that I listen to when I'm like working out because the pace helps a lot.
I see.
So and it's a wide range of music. I would say most types of music I listen to. Yeah, there's a place for like country western music, but maybe not in my music listening. So right. I mean, those songs can be fun, but it's not something I listen to regularly.
Fair enough. So you pick the genre of music based on what you're doing in the moment.
Yeah, absolutely.
I love it.
Absolutely.
I love it. I kind of employ the same philosophy.
There's lots of good music out there, right? And if you were a music appreciator and you understood music well, I understand why those people like so many different types of music. Because when you sit down and listen to a song, it doesn't really matter what the genre is. That song has lots of complexity to it. There's lots of layers.
You're listening to components.
There's components, and you appreciate those components as well. There's a musician associated with that instrument and a musician associated with that. Or maybe there's a guy on a synth playing a bunch of different things. But either way, somebody mixed that, somebody produced that. And so you get a much bigger appreciation for that. I feel like I in my early years of music listening, I didn't listen to music that deep. Right? I listened to music because it sounded cool and it reminded me of things. But nowadays, I actually think when I listen to music, if I give myself the opportunity to listen a little more carefully, I can start to pull out these little idiosyncratic things that makes that music style so appealing to people who enjoy that music style. I think if you look back at music, and we go way back, let's go hundreds of years back, where you had very complex compositions and very large groups of musicians doing it, you still had to have a good ear to appreciate what it was. But that actually, like classical music, I want to say that classical music is probably the type of music where I first realized that there are many different layers to music.
Yeah.
And not because the classical music was overly complex, although some of it is very complex. I mean, some classical musicians, like Mozart, for example, thought at multiple levels simultaneously when going through music, right? So there's lots of structure there. But even the more simplistic versions, you still had to have certain instruments play at certain times. Each one of them played off each other, and all of them were an ensemble that would play together. As time went on, we dropped the number of individuals in a band. Right? So we don't have like groups of 20 guys getting together or the 15 ladies playing the fiddle. Now we're getting down to the thing where, I mean, you get to one of my favorite groups, Rush.
Okay.
3 guys.
Yeah.
3 guys make all that complex music back when they were in their heyday. And so they had to play very layered. And that was but it's such a different way to think about music now, is that you have a small number of people providing a bunch of sounds as opposed to a large group of people each providing their own. And I think because of that, we lose the ability to pull apart those layers. So
I think that's a really well said observation. Definitely. Because when I was younger, like I was just listening to, small bands with many different instruments.
Right.
They're all doing multiple things. Right. And as I've become affiliated with the radio station and just older and started appreciating that older music, it's totally, you like peel back the layers of the song.
Right.
You know?
Right.
It's much different and intricate.
Yeah.
That's cool. For sure. Very cool. Awesome. Well, that's pretty much all I have for you. Thank you so much for making the time today to talk science, talk shop, and talk music. You're listening to episode 10 of What's New Wazzu. This is KZUU 90.7 FM. We're broadcast service at ASWSU. Thank you so much, Dr. Hinz. That's Hinz, not Hinz, because I know every one of his students thinks it's Hinz.
Yeah, you're all right.
I am that person. So it's Hinz. Thank you so much for your time.
My pleasure. Thanks for having me.